Hello everyone, let's look at next permutation. The problem statement is we need to implement next permutation, which rearranges numbers into the lexicographically next greater permutation of numbers. If it's not possible, we must rearrange it as the lowest possible order, and we want to do it in place. First of all, permutation is different from combination, as permutation is ordered ascendingly. For example, the permutation for 1, 2, 3, it should be 1, 2, 3, 1, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. We have these 6, and the sequence is ordered ascendingly. So we want to find the next permutation. For example, the input is 1, 2, 3, so the output should be 1, 3, 2. One solution is to use brute force. We can exhaust all possible permutations of the list and then find the item just larger than the input. However, the time complexity and space complexity would be bad, which is also against the rule in the question, which we need to make change in place. That's constant space complexity. Let's think how we can do it better. Because we want to find the next larger value for the given array, so we can first evaluate if the input array is already in descending order. If that's the case, we just return the reverse input. Like the second example, the input is 3, 2, 1, we just return 1, 2, 3. And then we want to loop through the input array from right to left. We want to find a larger value from right and swap it with a smaller value on its left. So we make the sequence slightly larger. Let me say this again. We want to loop through the input array from right to left. We want to find a larger value from right, swap it with a smaller value on its left. So we can make the sequence slightly larger. Be aware that this is not like other two pointers algorithm because we loop through the array twice to find those values. Let's look at the code, how we loop array twice from right to left to find these two indexes. Because we want to loop from back to front, and then we need to compare I and I plus 1. So the initial value for I is length minus 2. And after the loop, let's see if we have found this smaller value which is just smaller than its right neighbor. So if I equals negative 1, we can simply sort the input array ascendingly. If we have found this index I, so its value nums I is smaller than its right neighbor, and we don't need to worry about all the items on its left. Nums I is our smaller value, and we know from index I to the end of the array, they are in a descending order. And then we need to loop through the array back to front again to find the index j. So for this index value, nums j is just larger than our smaller value nums I. So nums j is just larger than our smaller value nums I, and then we swap them. After swapping, the sequence after index I is still in descending order. We just simply sort them ascendingly. Let's look at the code. And after this while loop, we have identified our index j, and then we simply swap nums I and nums j. And after this, we just do a sort from I plus 1 to the end of the array. Because right now it's in a descending order, we want to sort down ascendingly. So the left is I plus 1, right is nums minus 1, and then as long as left is less than right, we keep swapping. In this final while loop, we sort the array partially from left, that's I plus 1, to the end. And this is how we sort it in place. And given we have already implemented this sort, I think we can change the condition here. So we no longer use this inbuilt method. So the condition becomes if I is greater or equal than 0. And then we can move this outside. Or you can put this into a helper method. Let us submit. It passed. Let us look at the complexity here. Obviously, space is constant, and for time, it's n, because we have one while loop. Although we have looped it multiple times, but the time complexity remains O(n). If you have any questions, please leave a comment below. Thank you for watching.